Something extraordinary is happening on the sun right now, not in the distant, abstract way that space stories are often told, not as a quiet scientific curiosity buried in data that only specialists notice, but as a real event unfolding in real time with the potential to reach into the systems that modern life depends on every day. For most people, the sun is background. It rises, it sets. It lights the sky, warms the planet, and disappears from thought. But every so often, the sun reminds us that it is not just a source of light. It is a violent star. And right now, one particular region on its surface is drawing serious attention. That region is AR4366. In just a matter of days, AR4366 has grown from a dark blemish near the edge of the solar disk into one of the most unstable and closely watched sunspots of solar cycle 25. It is not only large, it is fast-growing, magnetically chaotic, and already responsible for a sequence of powerful eruptions that have pushed scientists, observers, and space weather forecasters into a state of heightened attention. According to the source material you provided, AR4366 rapidly expanded to nearly 10 times Earth's width while producing repeated high-end flares, including an X8.1 class event that caused major radio blackouts and raised immediate concern about possible Earth-directed impacts. And before we go deeper into this story, if you enjoy videos about space, cosmic disasters, solar storms, black holes, and the hidden forces that can change life on Earth without warning, subscribe to the channel and turn on notifications. This channel is built for stories exactly like this, the kind that start in science but quickly become about survival, infrastructure, and the uncomfortable truth that our modern world is more fragile than it looks. Because AR4366 is not just another astronomy headline. It is a reminder that we live under a star capable of doing far more than lighting our days. A reminder that one unstable region on the surface of the sun can interfere with radios, satellites, power systems, GPS, aviation, and communication networks. And a reminder that for all our technology, we are still deeply vulnerable to forces that begin 93 million miles away. To understand why AR4366 matters, you have to understand what a sunspot really is. A sunspot is not simply a dark mark on the sun. It is a visible symptom of an invisible struggle. The sun is not solid. It is a rotating sphere of plasma superheated ionized gas, whose charged particles constantly interact with magnetic fields. Deep inside the sun, its layers rotate at different speeds. The equator spins faster than the poles. Over time, that differential motion twists and knots magnetic field lines, winding them tighter and tighter like stressed cables under enormous tension. When those magnetic fields break through the visible surface, they create sunspots, regions where magnetic intensity suppresses the normal upward flow of heat, making them appear darker than the surrounding surface. But darker does not mean calmer. In reality, sunspots are often some of the most dangerous places on the sun. The source text describes them as pressure valves for immense magnetic energy, waiting for the moment when the field lines become too twisted to remain stable. And AR4366 is not calm. It is one of the most unstable magnetic regions currently visible. Its magnetic structure is classified as beta-gamma delta, the most dangerous category used in routine solar monitoring. That classification matters because it indicates a region where opposite magnetic polarities are crowded together in a highly tangled arrangement, creating the kind of stress that often leads to powerful solar flares. Your source material makes the implication clear. Regions with beta-gamma delta configurations do not usually settle down suddenly. They remain dangerous until they either exhaust their stored energy or reorganize into something more stable. And AR4366 appears to be doing neither. It is still growing, it is still adding new spots, it is still increasing in complexity. That is what makes this story so tense. This is not a sunspot that has already peaked and is quietly fading. This is a region that may still be in the middle of becoming more dangerous. And that matters because of what AR4366 has already done. According to the material in your file, this one active region produced 6 X-class flares in roughly 72 hours, plus a much larger number of M-class eruptions in between. X-class flares are the strongest flares the sun produces. They are not minor outbursts. These are the kinds of events that can ionize Earth's upper atmosphere, disrupt high-frequency radio communication across large parts of the globe, and in some cases launch coronal mass ejections, giant clouds of magnetized solar plasma, into space. The biggest of these came late on February 1, when AR4366 unleashed an X8-1 flare. That blast was one of the strongest flares of the current solar cycle and was powerful enough to trigger major radio blackouts over parts of the South Pacific. In practical terms, that meant communication systems that depend on the ionosphere, especially aviation, maritime, and shortwave radio links, were suddenly affected by the sun's activity within minutes of the flare. This is one of the reasons solar storms are so unsettling. The radiation from a flare moves at the speed of light. There is no meaningful warning delay. Once a major flare erupts and Earth is in the line of fire, the effects in the upper atmosphere begin almost immediately. And then AR4366 kept going. That is one of the most important details in this entire story, because a single major flare can always be dismissed as a dramatic but isolated event. A cluster of repeated X-class eruptions from the same unstable region is much harder to ignore. This is what gives AR4366 its identity, not just size, but behavior. Not just power, but persistence. It is acting less like a brief disturbance and more like a flare factory. Your source material uses exactly that idea. Amateur observers and astrophotographers describe AR4366 as a region that is crackling almost non-stop, still adding new intermediary spots, still evolving, and still showing signs that its magnetic system is reorganizing rather than calming down. One observer called it the most active sunspot of solar cycle 25. Another described it as just getting started, a chilling phrase when the region had already produced a barrage of major flares. These observations do not replace official data, but they add texture and urgency to it. They show that this is not only a numerical anomaly in reports. It is visually and behaviorally abnormal to people watching the sun closely hour after hour. And that leads to the comparison that has made so many people uneasy. The Carrington event. The Carrington event of 1859 remains the most powerful geomagnetic storm ever recorded. When it hit Earth, telegraph systems failed, operators received shocks, paper caught fire in some stations, and auroras appeared at unusually low latitudes, bright enough to make people think dawn had arrived in the middle of the night. In the modern imagination, the Carrington event has become a benchmark, the historical example everyone turns to when asking what a truly severe solar storm can do. Your source material draws that comparison carefully but clearly. It notes that AR4366 has already reached roughly half the size of the sunspot associated with Carrington and is still rotating into a more favorable Earth-facing position while continuing to produce major flares. That does not mean AR4366 will produce a Carrington-level disaster, but it does mean the comparison is no longer ridiculous. And in some ways, the world today is far more exposed than the world of 1859. Back then, global civilization depended mainly on telegraph wires. Today, civilization depends on electrical grids, satellites, GPS, aviation systems, internet backbones, precision timing, communications networks, fuel distribution, refrigeration, water treatment, logistics chains, and digital infrastructure woven so tightly into everyday life that most people do not think about it until it breaks. That is why severe space weather is not just a story about auroras or beautiful skies. It is a story about infrastructure. The source text does not soften this point. It describes a chain reaction scenario in which hospitals lose power, water treatment plants shut down, communication networks fail, fuel cannot be pumped, refrigeration collapses, and supply chains go dark. It explicitly frames this not as doomsday fiction, but as engineering reality in a system that was never designed to withstand simultaneous, multi-region transformer failures at large scale. The power grid has redundancy for ordinary disturbances. It was not built for a true extreme geomagnetic crisis. This concern is not theoretical. The source file points to a real historical warning: the March 1989 geomagnetic storm, which collapsed the Hydro-Quebec grid in about 90 seconds and left millions without power. That storm was far weaker than the Carrington event, yet it was still strong enough to show how vulnerable a modern grid can be when geomagnetically induced currents begin flowing through long conductors like transmission lines. After that event, Canada invested heavily in protective measures such as current-blocking devices and grid hardening. The source notes that the United States has moved more slowly and remains broadly vulnerable despite some monitoring and mitigation steps. It even cites a Federal Energy Regulatory Commission estimate suggesting that failure at only a handful of critical substations could trigger cascading consequences across much of the eastern United States. So when people look at AR4366, they are not panicking because a sunspot looks dramatic. They are thinking about systems. They are thinking about the fact that a star can interrupt aviation without touching an airplane, disrupt navigation without destroying a satellite, and place stress on transformers without ever physically striking a city. They are thinking about how civilization has become more advanced, but also more dependent, more synchronized, and therefore more vulnerable to simultaneous, invisible shocks. And that brings us to the second major threat beyond flares: coronal mass ejections, CMEs. A flare is a burst of radiation. A CME is something different. A CME is a vast cloud of solar plasma and magnetic field launched outward into space. If a CME is directed toward Earth and arrives with the right magnetic orientation, it can couple strongly with Earth's magnetosphere and trigger a geomagnetic storm. Not every flare produces a CME, and not every CME causes severe consequences. But when a fast CME strikes with a strongly southward magnetic field, the results can escalate quickly. That is what forecasters watch for. And AR4366 may already have sent at least one relevant shot our way. The source material identifies a CME associated with the X8. One flare and notes a forecast G1 geomagnetic storm watch for February 5 and 6, with concern that this initial forecast could prove too optimistic depending on what else AR4366 launches. In space weather terms, G1 is minor. It can cause weak grid fluctuations, limited satellite effects, and expanded aurora visibility. On its own, that is not catastrophic. But the larger fear in the script is not the glancing blow already in the forecast. It is the possibility that AR4366 continues erupting as it rotates into a more direct Earth-facing position. That is the key word here: position. So far, some of AR4366's strongest eruptions happened before the region reached the best angle for direct Earth impact. But as it moves closer to the center of the solar disk, the geometry changes. A flare that would previously have glanced away from us could become much more geoeffective. A CME that once missed Earth could now be aligned far more directly. That is why this is not just a retrospective story. It is an unfolding one. And the source text goes one step further, raising a possibility that is especially unsettling: the idea of multiple CMEs interacting. In 1859, the Carrington CME appears to have reached Earth in roughly 17 hours, an unusually fast transit that may have been helped by an earlier CME clearing out the solar wind ahead of it. The source material suggests that AR4366 has produced enough activity that, while multiple Earth-directed CMEs have not been confirmed, the possibility of interacting eruptions cannot be dismissed. If a faster CME overtakes a slower one, the result can be a so-called cannibal CME, a merged structure carrying more mass and magnetic complexity, potentially increasing its geoeffectiveness. The script is careful to label this speculative, but it also emphasizes that the possibility exists and that an initial mild forecast could look very different if additional eruptions occur. And that is what makes AR4366 so compelling to watch. It is not only dangerous in what it has already done, it is dangerous in what it still has the potential to do. The source text lays out a set of scenarios that make this uncertainty easier to understand. In the most moderate scenario, AR4366 continues producing more M-class and occasional X-class flares, with a sequence of minor to moderate geomagnetic storms over several days. That would mean intermittent radio blackouts, some GPS degradation, minor grid fluctuations, and perhaps repeated auroras at mid-latitudes. Noticeable, disruptive, may be costly, but not civilization-threatening. The source suggests this is the most likely path, assigning it roughly a 50 to 60% probability. In a more serious scenario, AR4366 produces a major Earth-directed X-class flare, launches a fast CME while in stronger alignment, and drives a G4 or G5 level geomagnetic storm. In that case, auroras push deep into lower latitudes, power systems experience wider disturbances, satellite operations suffer more serious problems, high-frequency radio becomes unreliable across large regions, and economic costs rise into the billions, with recovery measured in days or weeks. The source treats this as less likely, but still real enough to keep forecasters uneasy. And then there is the tail risk scenario, a near-Carrington or Carrington-like event, a flare comparable to or even stronger than the February 1X8. One eruption, this time while the region is in optimal Earth alignment. A fast, dense CME with strongly southward magnetic orientation. A transit time of less than 24 hours, possibly accelerated by earlier eruptions clearing the path. Extreme geomagnetic conditions sustained over a longer period, perhaps by multiple CME arrivals. Under that scenario, the source text describes transformer failures across multiple regions, power outages affecting tens of millions, cascading satellite disruptions, unusable GPS, and a communication environment pushed close to breakdown. The script assigns this a low probability in any given short window, but does not dismiss it as impossible. That probabilistic framing is important, because this is not a story where the honest answer is panic. It is also not a story where the honest answer is complacency. The honest answer is uncertainty under tension. AR4366 may weaken, its field lines may reorganize. Its eruptions may continue without sending anything truly severe toward Earth. The current storm watch may remain minor, and this entire episode may ultimately become an intense but manageable chapter in Solar Cycle 25. But the opposite is also true. AR4366 may continue to grow, it may continue to release energy at high levels, and as it moves into better Earth-facing geometry, the stakes rise. That uncertainty is not failure in science. It is the reality of trying to forecast the behavior of a star. One of the strongest sections in your source file is the part that explains what to watch for next. It notes that official forecast centers update their guidance multiple times per day, and that a shift from a G1 watch toward G2, G3, or beyond would signal a reassessment of the incoming CME's strength. It also highlights a crucial detail for severe storm forecasting: the BZ magnetic field orientation measured by satellites near the L1 point between Earth and the Sun. If that magnetic component turns strongly southward shortly before impact, geomagnetic intensity can jump quickly. In practice, that often leaves a warning window measured in minutes, not days. For grid operators, satellite teams, and communications planners, those final measurements matter enormously. That should tell you something profound about our relationship to solar storms. For all our models and spacecraft and instruments, some of the most important answers still arrive at the last minute. We can track sunspots, we can measure flare strength, we can detect CME launches. We can estimate arrival times, but the exact severity of an incoming geomagnetic storm can still depend on final magnetic orientation only shortly before impact. That is why stories like AR4366 feel different from many other natural hazard stories. There is science, yes. There is forecasting, yes. But there is also a stubborn unpredictability at the center of it. And maybe that is part of why the event is gripping so many people beyond the scientific community, because it strips away a modern illusion. We like to imagine that the systems around us are stable because they are engineered. We like to imagine that satellite navigation, digital communications, electrical grids, and continuous connectivity are simply normal features of life now. We forget that these systems exist inside a larger environment. Space is part of that environment. The sun is part of that environment. And when the sun becomes active enough, the line between astronomy and everyday life disappears. That is the deeper story of AR4366. It is not just about a sunspot. It is about dependence. It is about vulnerability. It is about the fact that modern civilization runs on invisible systems that can be stressed by invisible forces from 93 million miles away. Right now, AR4366 is one of the clearest reminders of that truth. It has grown unusually fast. It carries one of the most unstable magnetic classifications used in solar monitoring. It has already produced multiple X-class flares. It appears to have launched at least one CME associated with a geomagnetic storm watch. It is still growing more complex, and it is still moving into a more dangerous Earth-facing position. That combination is why scientists are watching. It is why amateur astronomers are posting constant updates. It is why comparisons to historic space weather events are being made at all. And it is why this story does not feel finished, because maybe AR4366 weakens tomorrow. Maybe the next CME misses. Maybe the current concern settles into a case study rather than a crisis. But maybe not. Maybe we are watching one of those rare moments when the sun reminds a technologically confident species that all its networks, all its precision, all its infrastructure still sit beneath a star that does not care how modern we think we are. And that is what makes this story so powerful. Not certainty, not even catastrophe, but possibility. The possibility that the most important event affecting Earth this week may not begin in a government office, a battlefield, a stock market, or a city. It may begin on the surface of the sun. And if this is the kind of story you want more of, real science, real stakes, and the hidden forces shaping our world, subscribe to the channel and turn on notifications. Because stories like AR4366 are exactly why this channel exists. To take events that seem distant, decode what they really mean, and follow them all the way from abstract science to human consequence. Because with AR4366, this may only be the beginning.